Yeah, this talk is mine, so I do not need to introduce myself in the beginning. So we can start today's discussion. My topic is from Pulsar to Lakehouse, building a unified streaming storage engine with Ursa. In today's keynote, Matthieu has already introduced an overview about how Ursa supported the Kafka and how Ursa supported the Pulsar engine. The only difference is that Pulsar used the bookkeeper or the write headlog storage, and Ursa just used the bucket. That is the only difference, and it brings another implication is Ursa will have higher latency because it needs bytes to write data to the bucket. But for Pulsar, we have bookkeeper, so we can achieve a very low latency for very latency sensitive use case. Yeah, this is about me. My name is Chen from StreamNative, and the director of storage. I'm the Apache Pulsar and the bookkeeper PMC member and the director of the StreamNative. And our goal is to design the next generation of storage architectures with Lakehouse integration. Yeah, let's come into today's motivation. And in today's keynote and the previous use case of all kinds of many customers, and we find as the time goes on and the increased usage of AI, there are a lot of data need to be analyzed and need to get more value from the data. So from the beginning of the data part is that we need a message queue to receive the data and write the data into the Lakehouse. That is the data ingestion. So from most of our case, there are IoT use case, and for example, the message from all kinds of device, and there are other user logs goes into our message queue, and they need a real-time analyze. And maybe the latency needs to be limited from seconds to minutes. And with this goal, we have many solutions. So first, I will introduce the solutions with the ETL later. And the next task is how to manage the data and how to make the biggest value of the data. There is another storage management format, Lakehouse. Currently, we have Delta Lake and also have the Iceberg. From the Lakehouse perspective, it provides in the lower layer, it has the data storage, the structured data, semi-structured data, and the unstructured data. And in the upper layer, it uses the metadata and governance. And in the upper layer is the application. We have BI, reports, and others. Yeah. Go to the data ingestion part. The main usage is Kafka, and another one is Pulsar. We have all kinds of connectors. For example, the Kafka Connect, the Pulsar IO connector, Spark, Flink, and other connectors. Those connectors consume the data from Pulsar or Kafka topic and do the schema conversion, then ingest it to the Lakehouse with the Delta Lake format or for the Iceberg format. But there are a lot of issues. Most of the issue need to be take care of the application side. For example, the expensive data silos. That you need to set up the connector with connect to the Kafka. and write to the Lakehouse. But they are two separate systems. And they are lead to the duplicated data and the inconsistent governance and the increased operational complexity. Another one is the complex ETL pipelines. And this issue becomes more complex when you need to deal with all kinds of schema. Because the Lakehouse is a schema system, and you need to pass the data with schema and map the schema to the Lakehouse and commit it to the Lakehouse. The third one is the high operational overhead. You need to manage extensive code infrastructure, and the repeated workloads leads to brittle system and ongoing result burdens. That means from the application side, what we need is to take care of your logic, your application logic. But there, you need to pay more attention of the lower layer of the system, how to ingest the data from the streaming system to the Lakehouse system. This makes the system more complex. Another one is that from the cost perspective, there are also a lot of challenges. I just take the Kafka, for example. In most of the deployment case, we need to deploy the Kafka into multiple zones to make sure there is no data loss, and the service is stable when one zone has been broken down. So in the first part, your application needed to produce data to the Kafka cluster. From the sending data part, you will introduce the inter-zone data transfer. Another one is, no matter Kafka or Pulsar, we have multiple replicas. And for Kafka, those replicas are stored in different brokers. That means different replicas need to be replicated between different brokers. You will introduce the interzone traffic. The third one is when you use a connector to ingesting data from a Kafka topic to the Lakehouse, you need to consume the data out and do a conversion from raw data to the column-based data, and then commit it to the catalog. It also introduced the cross-zone traffic and the connector management overhead. Yeah. So based on this motivation, we introduced Ursa. And for the Ursa design, we discussed a lot with our team. And we think it should work with our current Lakehouse industry. So we implement this system and share the idea into the paper and submit it to the VRDB 2025. And the good news is that this paper has been accepted and get the best industry paper award. Yeah. So let me introduce a little about our Ursa architecture. In the Ursa architecture, we support both Kafka API and the Pulsar API. This is only the protocol layer, so it doesn't matter how the lower layer implemented. From the middle layer, we have the two kinds of talent. One is the latency optimized talent, another one is the cost optimized talent. The main difference of these two kinds of talent is that what the lower layers rather head log stored. For the latency optimized talent, we use the bookkeeper or the Red Hat log storage. And for the cost-optimized talent, we use the object storage. That is what we discussed in the keynote. OpenAI's future plan is want to introduce the diskless implementation in their Kafka cluster. So our Ursa architecture provides two kinds of the implementation. The third part is how we ingest data from the Red Hat log into the Lakehouse. That is a common solution. No matter the Red Hat log is stored in the WAR, the WAR file stored into the object storage or into the bookkeeper. So today's discussion that I just wanted to discuss about how we support the data ingestion into the Lakehouse with the bookkeeper-based Red Hat log. That is what our Pulsar and storage engine use. And before I go through the next slides, I also want to explain a little about the Ursa. And Ursa, we introduced a key component that is the Oxia. Without Oxia, that the distributed high-performance metadata service, we cannot achieve our goal. And with Oxia, it is a central coordinator holding topic partition metadata offsets and the transactions. And another one is the string storage WAR and the Lakehouse. And the last part is the stateless brokers. OK, go back to the Pulsar. Let's go through how the current Pulsar implements the tier storage and why the open source Pulsar cannot integrate the data into the Lakehouse easily. With Pulsar, a few years ago, we introduced the tier storage. That is we call the open source Pulsar tier storage. With this tier storage, it just read the data from the bookkeeper and write it into the object storage, and then store the index into the media store. Currently, we use Zookeeper or Oxia. And there are some disadvantages. First of all, it cannot achieve the Lakehouse integration because those data are not parsed by the schema. So if you just want to read the data, you cannot bypass the broker because it is not an open format. It uses the Pulsar format. And the last part is also a very important part, is that the open source Pulsar offloader is not decoupled from the Pulsar broker. It runs within the Pulsar broker. So if you want to offload a large amount of data from bookkeeper to the blob storage, your broker service will be impacted a lot. So this is our current solution. Yeah. In Pulsar, we decoupled, in Pulsar's Lakehouse integration, we moved the whole comparison service out of the Pulsar broker. So if you wanted to offload a large number of data, that's fine. Let me explain the 3 steps of our current comparison service architecture. The first one is task generation. In Pulsar broker, we will batch the topic data into the task. For example, we will do a 3-minute batch or 256 megabytes per batch into one task. And as time goes on, we will publish a lot of tasks for different topics. This is the task generation. Another one is the distributed compaction. this runs in a separate comparison port. Those ports will acquire task one by one and read data from the bookkeeper cluster and convert the data based on the schema. Then give those tasks to the committer to commit it to the Lakehouse, to the catalog. At the same time, we will also commit the offset to the Ursa for the streaming read. That means with this comparison service, we can support only store one copy of data. Those copy of data can both support streaming read and the Lakehouse batch read. What's more, when the comparison worker reads data from the bookkeeper, we also can utilize the zone affinity. We will read the data from the local zone of the bookies. Yeah, this is the detailed explanation of the 3 steps: task generation, distributed compaction, and the commit. What I want to emphasize is that for the commit, we are not committed those tasks one by one. We will have a group. We will group hundreds of tasks in one commit and just commit them to the catalog. That will improve more efficiency. And in the last summit of the Databricks, the Asperg team introduced that they were focused on improve the commit latency for the streaming commit. So in our command service, we are a streaming engine. So we also will benefit from the streaming commit latency. In this part, we are do a group and to reduce the commit latency. Yeah. Okay. In the previous architecture, I introduced we can support one copy of data. Both support the streaming read by the Pulsar API, also can support the Lakehouse table API to do the batch read. And how does it work? That is a little interesting to introduce the Ursa stream format. In the right part of this slide, there are multiple header log objects. It is an abstraction. Those objects can be stored in the bucket or files. That is Ursa engine. Also can be stored in the bookkeeper. That is the ledger-based. Okay, but they have a common feature is that they are row-based data. What we do is that we will introduce a compaction service to keep reading those war objects and pass with the schema, and then write into the compacted object. By default, we will use a Pocket to store those files. And as time goes on, the compaction will continue to compact the newly added war object and compact it to the compacted object, that Pocket file. At the same time, we need to support streaming read. That is another interesting part. For the Pulsar API, we read a message with message ID. But after we compact the war object into the compacted object, it becomes those data are written into the column-based. How can we read those compacted data with the message ID? That is, we build an index from the offset to the message ID and stored in our metastore Ursa. So when a Pulsar consumer wants to read a message from the compacted object Pocket file, that's fine. The consumer will give the Pulsar broker a message ID. Okay? Pulsar broker will look up the message ID from the Ursa to get the offset and the Pocket file location. And then it will load the Pocket file and read from that offset and convert the data to the consumer. So that is how we support one copy of data to support the streaming read. Okay, for the batch read, how do we support it? That will be easy because all the Lakehouse product has two parts. One is data, that is the Pocket file. Another one is metadata. For Iceberg, it has their own metadata management. For Data Lake, also has their own format to manage the metadata. So only we have the data, and we can just commit those Pocket files to the Iceberg or to the Data Lake, and to build the Lakehouse table metadata. And then we can use the catalog to expose the data query. Any query engine just needs to talk with the data with the Lakehouse table API. Okay, let's use another few slides to go through how the word object compacted. In the beginning, the topic is a limited string, word object string from old to new. In the beginning, they are not compacted. Okay? When the comparison service starts, we will try to read data from the word object and do the conversion and write it to the Pocket file. As time goes on, we will read more object and then write it to the compacted object. Yeah, this is how we work. Another difficult issue we need to handle is the schema evolution. In yesterday's workshop, I also talked with many teams about their Lakehouse ingestion. And what they do is that they will write a Spark job or Flink job to read data from the topic and write it to the Lakehouse table. But the main issue is that you need to handle all kinds of issues. For example, bad records. Another is bad schema. What I talk about the bad schema is that the new schema data may be not compatible with the existing table. How can you handle it? So the common solution is that we introduce the DLT table. It means data later table. For all the common data or for all the good schema. The good schema means the schema is compatible. Okay, we will write the data into the data table. And for others, bad records or bad schema, we will just write it to the data later table. For the data later table, we passed with 3 fields. First field is message ID. Another field is the payload. And the last one is the failure reason. So when you write a message to the topic, but not find it in the data table, you can check the DLT table. And we will show why your message are being written to the DLT table. Yeah, what I wanted to emphasize is that for the bad schema, we adopt the Lakehouse schema compatibility check. So it means only if those schema are passed the Lakehouse schema compatibility check, and we committed the data to the Lakehouse, that table won't be broken. And that newly added the data can be read by the Lakehouse table 100%. Because in my testing, the Iceberg commit doesn't apply any schema check if you do not call the schema compatibility check. And you can commit anything into the Iceberg table. But when you read the table, you will find, oh, the table cannot be loaded due to the schema incompatible. So in this way, we can avoid any table corruption when you commit if you try to write any dirty data into the topic, and we can just find it and write those dirty data into the dirty table. Yeah. Another one is the catalog integration. In our Ursa, we write data into the Lakehouse, but if we wanted to make the data available in the third-party engine, for example, Presto or Polygraph or others, we need to register them into the Lakehouse. So currently, StreamNative won't build our own catalog. We will cooperate with the current Lakehouse catalog provider. For example, the Databricks Unity catalog, the Snowflake Open catalog, and the AWS S3 table. When we keep compacting data from the world object to the compacted object, we will try to register those compacted objects to the catalog. So we have two table modes. The first mode is the internal table. That means we just register the compacted object file to the catalog. Do not do any modification. That means in this mode, we won't support the upsert. Because in the CDC use case, those upserts need to delete the old key and write the new key. So in order to support this use case, we introduced another table mode named external table. The external table means it is external compared with the StreamNative, but it is managed by the catalog. So in this morning's the keynote demo, we created the Iceberg table into the Unity catalog managed Iceberg table. That is managed by the Unity catalog. So it is also external from the StreamNative perspective. And with this case, we can support the appends and upserts to the table. And I have another slide to introduce in detail what's the difference of the internal table and the external table. Okay. Another one, you may be interested of how Ursa interact with the catalog. In the first part, the left one is user. I just take the Unity catalog as an example. The user needed to create the Unity catalog in the Unity catalog UI and create the service principal and configure the storage bucket and related permission. And then you will get a credential. So the user will provide StreamNative Ursa engine, StreamNative cluster with the catalog name and the credential. That's fine. And the StreamNative Ursa storage will use this credential to talk with the catalog service. He will send a request to catalog service and get the table location and a temporary credential. When the Ursa storage gets the temporary credential, we will use this credential, write the Pocket file into the bucket returned by the catalog. Okay? After we write those data, the next step is commit. How will we commit to the catalog? We just committed the snapshot to the catalog service. And then catalog service will write the Iceberg or Data Lake table manifest file to the bucket, and then return the commit results. Okay, that's the whole process of how Ursa interacts with the catalog. Okay, maybe some customer will say, oh, your parser supports multi-tenancy. And one tenant also can have multiple namespace. And one namespace can also have multiple topics. And from our own service, we have different organization or different application. And we need to write to different catalog, maybe different catalog provider. And the different, that means the topic under different namespace will be isolated, and they cannot talk with each other. How does parser can support it? The answer is yes, because parser can support, in the beginning of parser, we support multi-tenancy. So we can configure the different catalog in the namespace level, or even in the topic level. Different topic can write to different catalog. So we can achieve the namespace or topic level data isolation. Okay, go back to the two table mode. One is the internal table, another one is the external table. For the internal table, that is one copy. Yeah, all the internal Pocket files will be exposed as a Lakehouse table. And those tables can be read back by the parser protocol. Another one I want to emphasize that the table's whole life cycle is managed by parser. That means if you set a retention policy on the table, and the parser will expire or delete those expired data. And the internal table is only append only, and you can use any query engine to interact with the catalog to read those data. But it is in the read-only mode. You cannot modify it. Another one is the external table. That it will has two copies. One copy is used for the streaming read. Another copy is used for the external table. So you can do anything as you want on the table. For example, run the table maintenance, rewrite data files, rewrite manifest files, expire the snapshot or clean up offline files. Okay, this is an overview of our streaming argument Lakehouse. In our architecture, we have many external data sources. For example, the database, the parser, Kafka, or even files. We use parser or Kafka streaming to produce data to the topic. And then our companion service will keep reading those WAR files and compact into the Pocket files. For the first one, the bronze table, it means the internal table. And for the silver table, it means external table, because you can do more motivation or do other optimization on that table. In the last one is the gold, and you can do any, because you can read from the silver table and generate from the gold, generate to a gold table, and then we can use the uni index to capture the CDC of this table and read back as a string. In the downstream, you can use the other system for the real-time applications or streaming system, streaming processing, or other AI analysis. Yeah, so this one is from the data from parser or Kafka to catalog. This is the data ingestion. And from catalog to parser, that is we can use we can interact with the catalog to read the data stored by the parser. Okay, this is the unified data products in one Lakehouse. That from the external data source, we have all kinds of all kinds of sources and write data to the streaming augment Lakehouse, and then provide the service from the applications. OK? Yeah. That's all from my today's sharing. And any questions?